So if you think back to momentum, and I know it's been a while since we've looked at it, momentum was a measure of how hard it is to stop something. And if you have momentum, you have mass and velocity. And basically, if you want to stop something that has mass and velocity, you have to put a force on it, and that force has to act for some time. And the area under the curve, the integral of force and time, gives you this thing called an impulse. And by calculating impulse, you can figure out how much your momentum changes. Angular momentum, the rotational version of momentum, works pretty much the same way. If something is spinning, you have to provide a rotational force in order to stop it. Rotational force, of course, is called torque. Angular momentum is basically just mv using rotational quantities. We have moment of inertia, I, instead of mass. We have angular velocity, omega, instead of regular velocity. Other than that, it works exactly the same. If something is spinning and you want to change its angular momentum, you have to essentially put a torque and have that torque act for a certain time. This seems like an exotic topic, but it's actually something you learned when you were a little kid first riding a bike. If you try to balance this thing on its own, it's very unstable. It just falls over. And that's like you when you first tried to ride a bike without training wheels. But the thing you learned early on was when you started moving, it became a lot harder to tip. And the reason for that, and let's get this thing going, is that you're giving it angular momentum. And just like a moving train requires a big impulse, a force applied for a long time, to stop, a rotating wheel requires a lot of torque. And this thing can go on its own for a fairly large distance. The way I introduce this to students in class is I give them this bicycle wheel, and I tell them to grab it with one hand and to put a torque on it. It's very easy to do. However, if you spin it, it becomes really hard to do. And that's because you're trying to change its angular momentum as you do this. Let's look at some examples of where angular momentum can be interesting. All right, so I have the spinning bike wheel again, and as you can see, I've taken off a peg so that the other side doesn't have a stable support base. And we're just going to set this down on the ground, back off, and watch what happens. So as you can see, it stays up. It stays pretty much pointed in the same position it was. And a device like this we call a gyroscope. And it's used to lend stability for things that we need to stay pointed in a certain direction for a long period of time. If that's going to fall over, the angular momentum has to be taken away by an impulse. Just like a freight train, to stop it, you would need to apply a force for a long period of time to cancel out its momentum. To cancel out this wheel's angular momentum, you'd have to apply a torque for a certain period of time. And that keeps it pointed upwards for a fairly long period. This is how we keep the Hubble telescope pointed at something. It's how we kept the Kepler telescope, which its job was to stare at one point in space for years, oriented on that exact point. When its gyroscopes broke, Kepler wasn't useful for its original mission. So you know that this makes a bike stable. Oh, there it goes. Finally, that torque has been enough that it's come to rest. This has been used to make many other things stable, including ships. So in that one, it may not be clear what direction you're putting the torque on. Turns out angular momentum is actually a vector too. We don't have to focus on this too much, but if we have rotation like this on this wheel, the angular momentum, depending on the direction you spin it, is either pointing straight out that way or straight back this way. So you are putting a torque when you tilt it. You're changing its direction in 3 dimensions. Guys, there's one more thing with the bicycle wheel demonstrator I want to show. If I just hold this by a string and I let go with my left hand, not surprisingly the bike wheel falls. And it does that for the same reason anything else falls. The center of mass, center of gravity tries to get as low as it can. But that's not going to be possible if there's angular momentum in the bicycle wheel. Because again, gravity exerts a torque, but you need an impulse in order to change angular momentum, which means it has to exert that torque for a while. And that results in kind of an interesting motion, which is called precessional motion. And we'll watch this thing precess as it tries to get to the lower position. So it's trying to get itself to the handle pointing down. But that's going to take a little while to happen. So you can see it's slowly spiraling towards having that handle be down. Angular momentum is a fairly complicated vector topic, and dealing with it fully in the several dimensions we have to care about is beyond the scope of any of the 3 physics courses we offer in high school. But I think it's interesting to see. All right, so now as angular momentum is decreasing due to friction, it's easier to do. And also, this impulse has been going on since I first started talking. So now we're finally getting to the point we'd be if there hadn't been angular momentum.